Hi, today we're going to do the second part of the weight mass because we're going to look at how your weight and your mass change in around the solar system. Before we can go on to look at weight and mass around the solar system, we ought to review what it is. So you should remember that your mass is the amount of matter in an object, the amount of atoms, the amount of particles. The more particles you've got and the bigger those particles, the more mass you will have. But your weight is the force of gravity pulling you towards the Earth. If you've got the mass as the number of particles, wherever you go in the universe, your mass will not change. Your mass will stay the same. Same number of particles down here, same number of particles on Pluto, wherever you go, providing you're not binge eating or doing your poos. But depending on where you are in space, depends on the pull. There is nowhere in space that you will not have a gravitational pull. Value of G will be something, but it will be different. So what we've got here is we've got a table. It shows the planets, and you can tell me why the moon and Pluto are in brackets. It's got the value of G. We tend to say G because gravitational field strength is a big word. Remember that this value of G is the strength of gravity, and it is in newtons per kilogram. And these are the values, or the approximate values, for places in the universe. Here you've got a column to fill in about your mass. Remember we said wherever you go your mass stays the same. So you can either go away, find some scales, stand on them and record your mass, or you can make it up. If you want to make it up, 50 kilograms is a good value. On the next sheet I'm going to give you an example because we're using the same equation we used last time. Weight is mass times gravitational field strength, but this time we're going to change the value of G. Hi, so let's try an example. So I've cut a bit of my table out here. That Mercury, the planet, has a value of gravitational field strength of 3.7 newtons per kilogram. So every kilogram of your mass, you will have a weight of 3.7 newtons. So we know that weight is equal to your mass times your gravitational field strength. And if my mass on the Earth is 50 kilograms, then we know that wherever you go, your mass stays the same. So on Venus, it will be 50 kilograms. On Mercury, it will be 50 kilograms. So therefore, my mass is 50 kilograms. You can enter there whatever you want to put in for your mass. You don't have to tell me the truth. So that's 50 times 3.7. And I'm not expecting you to not do that on the calculator, although you can. The best way to do it is times by 100 and then divide by 2. That's a quick way of multiplying by 50. I get that as 185 newton. My weight on Mercury would be 185 newtons. If you want to round that up to the right number of significant figures, I'd actually put 190. So that's how you're going to do it. You're going to fill in the table, neater than me. So on Mercury, I would have a smaller weight. Hope that helps you. And this page is to copy out this diagram. You can make it neater if you want. Please be aware that these are nowhere near to scale. Almost impossible to have a scale where the sizes and the distances are on the same scale. So copy this into your jotter. I want you to write below your mass on each of those planets and places. And don't forget the moon here. Also add your weight at the surface of any of these planets. And this is what needs to be uploaded to your assignment. Thank you. What I forgot to mention is last week we talked about inertia. And inertia is related to mass. And inertia tells you that an object wants to either continue in its motion. So if it's stopped, it wants to stay stopped. If it is moving, it wants to continue moving. The more mass, the harder it is to start moving, the harder it is to stop moving. And here's a little demonstration you could try at home. Notice meter is spelled M-E-T-R-E. How cool is that?
Have you wondered what it would be like to be an astronaut floating around in the space station? But why are the astronauts floating? I'm here at the Powerhouse Museum in Sydney to find out if anyone knows the answer. Why are they floating? No gravity?
No gravity.
Zero gravity.
There's no gravity.
Gravity?
The stuff that holds us to the planet when we spin doesn't happen up there.
Gravity holds you down, so in space there's nothing there, so you just float.
There's no gravity in space.
No gravity, there's very little.
But is there really no gravity in space? After all, the moon orbits the Earth due to gravitational attraction. So, where would the space station fit in this picture? Can you make me a roughly to scale model of the Earth and the moon? And then we're going to position the space station in there. So about like that?
Yeah, now there's...
Close up, maybe. About there.
You ready to see the real distance? What do you reckon?
Oh, okay.
Actually, about here. Maybe a little further.
I think we were wrong.
Now, if the moon is here and the Earth is there, whereabouts would you put the space station?
Somewhere around here.
Really?
About halfway?
Yeah.
Right about here? So that's maybe like a quarter of the distance to the moon. Let me show you the real distance. You ready for the real distance? The space station is right about there.
Oh, okay,
Right
that
there.
close.
Wow.
We're not good at this game.
The space station is actually only about 400 kilometers away. So if you're in Sydney, it's a little further than the drive to Canberra. But does it make sense that the Earth exerts a big gravitational force on you, but nothing on the astronauts just a short distance away? You reckon there'd be no gravity there?
There's not much. They float. We've seen them.
Well, clearly there's not. They're floating around.
I know they float, and the question is why?
No idea. I'm really confused.
Well, in truth, the force on the astronauts is almost as much as the force on you. So then, why are they floating while you're stuck here? The answer is the astronauts aren't floating, they're falling. Ah! And not only that, but the space station they're in is falling as well. Ah! So why doesn't the space station come crashing into the Earth? Well, the reason is the space station and astronauts inside have this huge sideways velocity of about 28,000 kilometers per hour. So even though they're falling towards the Earth, they're going so fast that as they fall towards the Earth's surface, it curves away from them. If the Earth didn't put a gravitational force on them, they would fly out into space.
Sure, yeah.
Right? So it's due to that gravitational pull that they can actually keep orbiting the Earth.
If it was to stop moving, it would be plummeting.
Exactly.
But would they...
They would still feel weightless until you smash into something. So the space station and the astronauts inside are constantly accelerating towards the Earth's core, but they never get any closer. And because they're accelerating at the same rate, the astronauts feel weightless. They have this amazing sensation of floating.
Our recent Christmas lectures were all about human space travel. So obviously we had to talk about zero-G and weightlessness, which are some of the most fundamental experiences of being in space. And this led to some discussion in the office about about what weight is. And I thought it'd be good to unpick in a video some of the issues that came up, because actually I think there's a lot of subtlety, dare I say it, some confusion in the way that people generally talk about the physics of weight. And one of the biggest misunderstandings is around the use of this term weightlessness, which lots of people assume means that in space you don't have any weight. But this isn't true. And this misunderstanding isn't because the definition of weight is confusing at all. It's actually really simple. And exactly as you learn it at school, weight is just the force on an object due to gravity. Or if you want to be more precise, it's the size of the gravitational attraction between me and the Earth, or the ball and the Earth, or this cup, or this chicken and the Earth. The problem, I think, is that the way we learn about weight at school doesn't really quite capture the way that people think about weight and experience it in real life. As I sit here, I would say that I can feel my weight bearing on my feet and on my bum, even inside my body. But is it really my weight that I'm feeling? Remember what we just said, that my weight is just the force of attraction between me and the Earth. But there's clearly a lot of stuff in between me and the centre of the Earth. The floor, the ground, a load of magma. And as the force of gravity pulls me down, repulsive forces are set up within all that stuff and at the interfaces between all of those objects. And these are intermolecular and interatomic forces accumulating all the way to the centre of the Earth. And the end result of that is that I just sit here, not falling. Those forces oppose and counteract the effect of gravity. So the really important point here is you don't actually feel your weight either. It's all of these other forces that support you that you experience as weight. This is where the confusion comes in. When we use the term weightlessness in the context of space and astronauts, we aren't talking about an absence of weight itself, but instead an absence of what you experience as weight on Earth. In other words, the absence of those opposing forces that support you. And confusion around this has led to another common misconception, that there is no gravity in space. But gravity is everywhere. The universe is filled with gravitational fields. You can't escape them. So the idea of being weightless due to the absence of gravity makes no sense at all. Interestingly, the effect of the Earth's gravity doesn't actually change that much when you go into space anyway, at least into low Earth orbit, like the astronauts on the International Space Station. The altitude of the ISS is about 400 kilometres, which sounds a lot, but it's actually only about 6% of the radius of the Earth. So gravity there is almost as strong as it is on the surface. What's really happening in space is that there is just nothing to counteract the effect of gravity. There are no opposing forces to hold you up, so instead you just fall freely. So with the ISS, which looks exactly like this, and with all the astronauts inside, this is exactly what's going on. It's not floating or hovering, it's just falling like anything else towards the centre of the Earth. It's just going so fast that it overshoots and overshoots and overshoots, till eventually it finds itself back where it started and goes round again. So weightlessness is just a state of unopposed motion under gravity, and all you need to do to create weightlessness is drop something. And when you do that, you remove all of those opposing forces and the object falls. And this is how we can create temporary weightless environments, like in aeroplanes like the Vomit Comet, which deliberately fly along paths to simulate freefall. So I think that the difficulty that people have reconciling this formal definition of weight with ideas like weightlessness comes from this conflation of these two slightly different ideas. On the one hand, you have the weight that you learn about at school as a gravitational attraction. On the other hand, you have this slightly subtler idea of weight as something you experience and feel. And in the Christmas lectures, we really wanted to get into this equivalence between freefall and weightlessness. And I think physicists would normally say that weightlessness is a consequence of freefall. But maybe with this view of weight, it would be better to say that freefall is a consequence of weightlessness. That is, as soon as you stop exerting other forces on an object, it has no choice, like Wile E. Coyote, but to fall under gravity.